Hello everyone, I'm Xiangli from Tsinghua University. I will talk about FLAIR, a fast, secure, and memory-efficient distributed analytics framework. Nowadays, users tend to outsource the computation to the cloud, using frameworks like Hadoop, Spark, and Flink. However, the cloud could be compromised from both inside or outside, and the attacker can even control the whole system. In that case, both integrity and confidentiality could be compromised. So to provide such guarantees, we have two choices. We may resort crypto method like fully homomorphic encryption. Unfortunately, it's too slow to use in practice despite its provable security. A practical alternative is trust encryption environment. There are some commercial products like Intel SGX and AMD ICV. Typically, CPU is the root of trust, and we can extend the trust from CPU to memory, creating a trust region called enclave. Owing to the hardware-enforced isolation, the code inside the enclave is guaranteed to correctly execute, and the confidentiality and integrity of data is also guaranteed. However, since the code is loaded from outside the enclave, the attacker may load malicious code and create a fake enclave. The integrity of code is not preserved. To defend against it, teams provide remote attestation for clients to ensure that the right code runs in the right hardware environment. Moreover, when data leaves CPU, it will be transparently encrypted by memory encryption engine, protecting the data from physical attacks like probing the memory bus. However, using TEs to protect Spark also has some challenges. We can see that once data leaves cache, it's encrypted and authenticated, so the cache miss overhead is larger. And given that T is the isolated environment, we first need to copy the data into the enclave, and then can we start execution. And finally, we need to copy data out, so the domain switch overhead is large. If we want to reduce data copy, we need to put more code into the enclave, which leads to large TCP. More bugs will be contained in the enclave to be exploited by attackers. What's more, TEs also suffer from various side channels like access pattern-based side channels linking the plain text. Typically, trivially putting the whole spark into enclave has all the issues except domain switch. Flare tries to solve all challenges. To avoid large TCP, we propose a minimalist philosophy, that is, we only put necessary code into the enclave. To reduce domain switch overhead, we propose new abstraction called shadow operators and explosive fusion. And we also propose memory-efficient process techniques to reduce the frequency of cache misses. Note that the minimalist philosophy also contributes to the goal to defend against chat channels while giving consideration to the performance overhead. Flare supports two modes. The stronger mode is oblivious mode. Now we show the workflow. First, user write program with Spark API. The program is compiled with Flare to generate two binaries for both trust domain and untrust domain. During the execution, Flare creates RDDs one by one, following the user program. When a job is triggered, the scheduler builds tasks and dispatches them to the worker. To run the task in the enclave of the worker, we only put operators inside the enclave, called shadow operators. This is our new optimizations that will be explained in details later. For each RDD, there is a shadow operators inside the enclave. Large amount of code stays outside the enclave, thus shrinking the TCP and following the minimalist philosophy. The worker invokes and fills the operators in enclave to do a task called shadow task. We also put the expected job DAJ into the enclave for the actual execution DAJ to check against. Since we follow the minimalist philosophy, we have reduced the TCP. Besides, we also reduce the cache miss rate as well, because the code size in enclave is smaller. However, when we only put operators into the enclave, One trust operator map should support different map instances, for example. The trust operator are unaware of the data types and function closures the user specifies. Therefore, during the execution, we should serialize data before transferring it across the encode boundary. We should also tell the encode the corresponding data type and the closures to deserialize data and run the computation in an interpreted manner. So the cost of cross-encode boundary serialization exists. Moreover, if we invoke the operators for every RDD, for example, when executing the first RDD, we should take the round to transfer the data, and for the second RDD, we need another round. Operator fusion is difficult in this case because the first operator does not know what the second operator should do. Thus, repetitive data transfers are needed. So, to solve those issues, our key insight is that we can embed the user-provided data type and closures into the operators to customize the operators called shadow operators. For example, we have different trust map instances customized for each invocation. Thus, the data can be directly transferred without serialization because both domains know the data type and the function closures. Thanks to the shadow operators, the computation can be easily fused because each operator already knows what it should do before execution, and the dependencies, the predecessor and successor information are also embedded in the shadow operators, and only the operators belong to the same task can be fused. Now the domain switch only occurs twice per task. Next, we will introduce our memory-efficient processing to reduce the cache miss penalty. So the best way to reduce the cache miss rate is to confine the computation to cache. Given that there are two kinds of dependencies in Spark, narrow dependency, which exhibiting one-to-one dependency. For example, the map operator will create narrow dependency, and the shuffle dependency, which exhibiting all-to-all dependency. For example, the group by key operator will create shuffle dependency. Moreover, shuffle dependency is further divided into shuffle right for bucket generation and shuffle read for gathering the bucket. And our key insight is that we can just adjust granularities for different dependencies. For narrow dependency, we propose block level streaming. That is, we process one block for every operator each time. Block is the encryption unit. If the block is smaller, the encryption overhead could not be amortized. However, we notice that for narrow dependency, the function can be arbitrary and the data would expand. If the block is bigger, it may violate the requirement. So we empirically set the block size to be 64 kilobytes. For shuffle dependency, we observe that the data would not expand during computation, so we use subpartition, which contains several blocks as a new granularity. On the one hand, if we use larger subpartitions with small blocks, it may directly exceed cache size, so the number of blocks a subpartition contains would not be too many. On the other hand, if we use smaller subpartition with fewer blocks, given that each subpartition generates, for example, two buckets, so there will be more buckets. To group the items in the order, we need to fetch blocks from each bucket the first time we do shuffle read. So we need to fetch too many buckets when combining buckets, exceeding the cache size. So we set the subpartition size comparable to last level cache. Besides, we found that different operators may have different scalability. For the first map, more threads cause even worse performance, while for the second map, more threads bring benefits. After we dig in, we found that is likely relevant to memory allocation. If the memory allocation is intensive, the multi-threading speedup would degrade. Therefore, we propose allocation adaptive prioritization. We divide the task into several phases. If the phase is memory allocation intensive, we just disable the prioritization. Otherwise, we enable the prioritization. Besides the previous discussed optimization, we also propose several other techniques in Player. First, we use cooperative guards to guarantee the execution integrity. Specifically, local guards are distributed in each worker and record the execution information. The global guard collects the information, analyzes it, and checks it against the expected drop DAG. Also, for side channels, we support oblivious mode, which adapts the techniques in opaque. Given that some of the techniques we introduced before are not oblivious, we should adjust them to be oblivious. For more details, please see our paper. And here is the evaluation setup. I emphasize the secure baselines here. Opaque is a previous design following minimalistic philosophy. The rest of two are the other design philosophy, monolithic philosophy. We implement a baseline called Vega Oculum, where Vega, a Rust version Spark, is directly put into enclave with SGX level S called Oculum. SGX PySpark is also a monolithic design putting PySpark into enclave with SGX level S. And here is the overall performance comparison. We test on both small data and large data. Since previous work do not have memory-related optimizations and they run too slow on large data, we only test them on small data. Even on small data, we achieve hundreds of times speed up than previous work. One of the reasons is the language advantage of Rust versus Java or Python. Nevertheless, even when we exclude this factor by compare each secure design with their corresponding insecure design of the same language, it still achieves 5.4 times speed up than opaque, thanks to the shadow operator abstraction. And for large data, we perform better than the LabOS method due to our memory efficient processing. We run slower than the insecure baselines most of the times. However, Flare performs better than Spark sometimes due to language advantages. We also test our oblivious mode, which incurs additional 6.5 times overhead. To summarize, Flare is a distributed data analytics framework for secure computing. We adopt minimalist philosophy to reduce TCB, and we propose shadow operators and shadow tasks to reduce the domain switch overhead. We also design memory-efficient processing to reduce the cache miss penalty. And finally, we enhance the security by providing oblivious mode. Thank you.